So galaxies rotate faster than their mass should allow. So I should say their observable mass. Should allow. So they rotate faster than they should be able to. Okay, so that leads us to come up with something called dark matter. So what is dark matter? Dark matter is mass that exists in the universe that does not interact normally with light and other particles. Okay, so it's stuff that does not interact normally with light and other particles. Okay, specifically light. The reason it's called dark matter is because we can't see it. We look out in the universe and we don't see any extra mass there. So it's mass that should exist but does not seem to exist just by looking at it. Okay. So a big thing we want to be able to do is we want to be able to talk about what each of these different things could be. And here is the list. WIMPs, sterile neutrinos, neutralinos, asymmetric dark matter, axions, mirror world dark matter, SIMS extra-dimensional dark matter, and composite dark matter. So we're going to go through each of these one at a time. You will need to add them to your notes so you have them. Okay? You should be able to give me a really simple explanation on these. You do not have to be perfect, and you don't have to give me a detailed explanation. Just a simple one. So don't feel like on the test that you have to be able to tell me in depth how we're researching all these things. Okay, we're just going to go through and do the basics of what do we think they are. Now, here's the biggest thing I want to point out before we do anything else. We don't know that any of these things exist. We don't know. These are just ideas that we came up with to help us explain what we're looking for. All right, let's start in the front. Let's start with WIMPs. Tell me what WIMPs are. Okay, so let's start with what they mean. So WIMPs are weakly interacting massive particles. Weakly interacting mean they don't interact with stuff the way you normally expect them to. So they just travel through space on their own, doing their own little beeswax, not interacting with other things. The only reason you know that the desk is in front of you is because you see light interact with it. Light hits the desk and bounce off. If light didn't hit the desk, you wouldn't know it was there until you touched it, in which case it would interact with your mass. But what if it didn't interact with your mass? Well, then you would have no idea it was there. You wouldn't feel it. You wouldn't see it. There would be no way for you to detect it to be there. Okay? How do you know that air's there? You can kind of feel the effect it has on you, but if you're just holding your hands in space, you don't know that air exists. You have to do something to get it to interact with you. That's kind of the idea. All right, so they're weakly interacting massive particles. What else can you tell me about them?
They're significantly heavier than regular particles like protons.
Yes. So they're very heavy and don't interact with stuff. All right. Put a star next to WIMPs. You absolutely, definitely should, for sure, definitely know what WIMPs are. WIMPs are one of the more important ones because they're they're the overarching category of what we're thinking. So WIMPs are what we describe as some of these other things. Some of these other things would fall into the weakly interacting massive particle category. All right. Sterile neutrinos. Franchette, what you got on sterile neutrinos?
Massive particles that shapeshift from one type to another.
Okay, so they are a fourth type of neutrino. We're going to talk about neutrinos next unit. So they're a fourth type of neutrino, and the reason why that's significant is neutrinos are nearly massless. They have almost no mass to them. But there seems to be something missing. There's a missing component to neutrinos. When we add up all the types of neutrinos, they don't equal 100%. There's something missing. And seroneutrinos are this fourth type of neutrino. And it doesn't interact, and it doesn't seem to interact with anything. We can't really find this. It's the fourth type of neutrino that seems to be missing. Okay. The reason why this is interesting is we have an idea that they should exist. We haven't detected them, and we don't know how many there should be. So it could be that there's so many of these things that it makes up for that missing mass. They're nearly massless, but there might be a large number of them. The problem is they don't interact with anything, and that's a problem. But they might interact with stuff and turn into things that we can detect. So we're optimistic that we can detect sterile neutrinos, and put a star next to these ones as well, because these are another one that we're really looking at and that we're trying to detect. All right, in the back, neutralinos. Solus, what can you tell us about neutralinos?
So everything has like a partner, and it's technically a WIMP, but it's polluted off observation. And it's based off of the idea that everything has like a super partner and it's bigger than
So it's a type of WIMP. And it's called a supersymmetrical particle. Okay, and it comes from something called supersymmetry. And basically, supersymmetry is this idea that every particle has a supersymmetric particle that goes with it. It helps fill in some gaps in the standard model, which we'll talk about the standard model a little bit later. And it's it's a weakly interacting particle. It's hard to detect. Let's see, is there anything else I'm going to point out? And neutralinos are something we're looking for because not only would it be a possible dark matter thing, but it would also prove this supersymmetry idea. And again, just to tell you what supersymmetry is again, basically every particle has a super partner that helps like fill in some of the gaps in the model. So it's basically supersymmetry. So it's a partner of a regular particle. So if this thing existed, we could prove several different things with it. All right, in the back, asymmetrical dark matter.
Asymmetry in the number of densities of particles and antiparticles.
Okay, so at the beginning of the universe, there should have been as many particles and antiparticles. Say antiparticles are just the opposites. And there should have been the exact same number as each other, but that didn't seem to be the case. There doesn't seem to be as much antimatter as there is matter. So maybe that also happened with dark matter. So maybe the same thing happened with dark matter. Maybe dark matter is some particle that didn't get wiped out at the beginning of the universe. So maybe it's leftover particles that didn't get annihilated, just like matter is leftover particles that didn't get annihilated. So leftover from the formation of the universe. All right. Axions. Where are my axions? You guys are axions, right? No. Y'all are axions? Okay, in the back. What are axions?
Axions are the strong nuclear force in a particle complex, and I think that if they can prove that they find that axions exist, that will either prove that they are what we call dark matter, or that they are related to dark matter.
Okay. So it helps explain the strong nuclear force, which we'll talk about next unit. They're a little bit different, and then they're already predicted to exist. And they would explain two things. They would explain the strong nuclear force, and they would explain dark matter, because they should be fairly large. Put a star next to axions. Axions are another big one. So WIMPs are the main idea behind this. Sterile neutrinos are something we think should exist and we've been looking for, and we're looking for them a lot. Axions are also something we think should exist, and we've been looking for them quite a bit. Good.